So anyway, just this morning I uploaded a revised version of what to expect for exam 1. So I added some stuff in there about, how do you take exam 1? It's going to be in Lau Lima and test and quizzes. And you'll need a password. So I'll send an email out later today. So if you're going to take the exam tomorrow, you need to email me and I'll email you the password. I won't do that until the morning. And then there'd be a different password for different times of the day and all that kind of stuff. So anyway, yeah, you will need a password. So if you get a chance, look over that, what to expect. And if you have any questions, let me know. Does anybody have any questions about anything in Unit 1?
I had a question from the last homework that we submitted.
Uh-huh.
And it's on question number 7. And when I was doing it, it's actually a question about the significant figures of this problem.
Oh, okay. Question 5, number 7. Homework 5, number 7. Oh, yeah, okay.
So when I was looking online and the final answer was, it looks like E. When I was doing it, I thought maybe the significant figures of the answer would be a bit different since there are only 3 significant figures in the percentage of abundance for O17.
Yeah. So there's only 3 significant figures.
So then
would occur, the uncertainty would occur in the 0.00647 in that 7 position. So you see the uncertainty there? It's plus or minus in that position. I didn't round off there because you don't round off until the very end. You see my point?
Yeah, where was could you say that again? Where was the uncertainty in that one?
In the answer, it's going to be at 0.00647 in that 7 right there, which is plus or minus 0.00001. But I didn't round it off right there. I didn't round off until the end.
Okay.
Yeah. I think that's probably your issue.
Thank you.
Mm-hmm. Okay, well, let's get into, not that one, chapter 5. Kind of a short chapter. It's an interlude between different kinds of materials, so it's kind of a good thing. So Lavoisier published somewhat of a periodic table. Some other guys did as well, but Dmitri Mendeleev was the one who got the major credit for this because he was able to predict that certain elements would then be discovered that had certain properties. So he's the one who really put it all together, and then his periodic table was validated after they discovered all these different elements. And so anyway, so the periodic table is not a spreadsheet, but it's not just a table or a chart, because if you go down a group, there's my periodic table. If you go down a group, which is up and down, those elements have similar properties. Not the same properties, but similar properties. Just like people in the same family might have similar properties, but they're all individuals. So if you know something about, say, hydrogen, you can kind of know something about all the other elements in that group. Okay. So say sodium. Look at sodium, it does a +1 charge. That's all it does. Sodium is either found as an element with no charge, or you can see it forms that +1 charge. That's all it does. If you look at all the other elements, they also have the +1 charge. So every element from that group likes to lose 1 electron. And when it does that, it has the same number of electrons as one of the noble gases. And what do we know about noble gases? Is that they're stable, they don't react with anything, not even themselves. And so in a way, if you're over here, you're going to lose electrons to be like these noble gases. If you're over here, you're going to gain electrons to be like these noble gases. So that explains a lot of the behavior. And so some of that is evident in what's called periodic law. So I'm going to show you a little bit of periodic law. What I did is I took the elements and I just numbered them across. So starting with 1, and then 2, then 3, until I ran out of space. And I also put the electron dots over here. These are called Lewis electron dots right here. Those are the valence electrons. And those are the electrons that are reactive. Valence electrons are the ones that are gained or lost or shared. And it's way ahead of the game, but I put it there anyway. So group 1, they have 1 valence electron. Group 2, assuming this is also group 1, group 2 has 2 valence electrons. Group 3 has 3 valence electrons, and 4 and 5 and 6 and 7 and finally 8. Nobody has more than 8 valence electrons. So then I just put them in a row. And then I reacted them with something extremely reactive. Chlorine gas is extremely reactive. If you breathe chlorine gas, you kind of become dead. It's very toxic because it forms hydrochloric acid in your lungs and will simply destroy your lungs. So in other words, I took all the different elements and I reacted them with hydrochloric acid and I wrote down what we would get. So with hydrogen, you would get HCl, which is hydrochloric acid. Then the very next one, element number 2, I cannot get it to react. No matter what I do, I can't get it to react. Then with lithium, I get lithium chloride, which is a 1-to-1 compound, just like this one is. And both of these act like they're ionic compounds. What that means is you dissolve them in water and they conduct electricity because they form ions. And the next one is beryllium. I get a 1-to-2 compound, and then a 1-to-3 compound, then a 1-to-4 compound. And these over here do not act like ions. They're more like covalent compounds. Then I get a 1-to-3, a 1-to-2, and then a 1-to-1, and then I can't get it to react again. So you see these properties are repeating themselves, aren't they? Then with sodium, I get a 1-to-1 compound that acts ionic. Then magnesium, a 1-to-2 compound that acts ionic. So how do we arrange the periodic table? Well, I took all this row over here and moved it underneath hydrogen because hydrogen shares that same property. Then I took all the next group over here and put sodium underneath lithium. So now you have hydrogen, lithium, and sodium. They're all in the same group because they have that similar property. Then helium, it's like, well, it doesn't really have a place to go there, but you put it over neon, because those share the same properties, which means that they don't react with anything. So the periodic table was put together with this in mind. It was a very practical organization. Chemistry, in fact, is practical. So now, if you know about helium and neon, what can you tell me about radon? Radon gas is at the bottom right there. It's along with all those other noble gases that don't react with anything. So you would expect that radon would do what? Good answer, nothing. What about francium? What would you expect francium to do? It's in group 1 with sodium. It's going to form the +1 ion. So the point is now that it's not something that you can use to calculate. It's not a spreadsheet, but it's more than just a table, because where that element is on the periodic table tells us a lot of information. So how do we organize the periodic table? Well, one is we talk about representative versus non-representative elements. So representative elements, also known as main group elements, obey most of the rules. So that's these two over here, and these 6 over here. In other words, you see this lower line right here. If it's sticking up over here, these are representative elements, and so are these. And the non-representative elements don't obey all the rules. They're also called the transition metals. Well, why? Well, here they follow all the rules, then they kind of follow some rules, and over here they stop following many of the rules. Then they start to follow the rules again, and then they follow the rules. So it's a transition between following the rules and following the rules. And they happen to all be metals. Okay? So that's why they're called the transition metals, the non-representative elements. So another way to organize it is with nonmetals versus metals. So this thick line right here represents the demarcation between the nonmetals, and the rest of them are metals. You can see that almost all the elements are metals. So the one thing that's out of position is hydrogen. Okay? Hydrogen is actually a nonmetal. Most of, I wouldn't say, not most, it's the opposite. I have seen periodic tables where they put hydrogen not here, but over here. Because hydrogen could just as well be in group 7 as it is in group 1. Because hydrogen, if you look at its oxidation numbers, hydrogen can do the +1 and the -1. It was first discovered to do the +1. Therefore, it was put over here. But because it does the -1, just like all these other ones, it could also be over here. And so these over here are also called the inner transition metals. The reason is these were taken out of this area right here. Okay? They did that to make the periodic table more narrow and to be able to line these elements up into particular groups. And so we also have some that are right on the line right here that we call metalloids or semi-metals, because they have some of the properties of a metal, some of the properties of a non-metal. And so the words are down here, but what I'll say is this. In your everyday experience, what do you know about aluminum? Notice aluminum is right here. Aluminum in every way acts like a metal. It's shiny, it's silvery, it reacts with oxygen, it conducts electricity, it's malleable, you can hammer it into different shapes. That's why it's not listed as a semi-metal. So notice that silicon is a semi-metal. These are called semiconductors as well. So aluminum over here is an excellent conductor. Over here is a non-conductor. But some of these that are right on the line right here conduct electricity under some circumstances and not under others. This is the reason why silicon and germanium and arsenic and all these kind of things are very valuable in semiconductors or computer chips. So here's some of the properties. The metals lose electrons, they're shiny, they're malleable, which means you can shape them into different things, and they're ductile, which means that you can make them into wires, and the reason why you would do that is because they conduct heat and electricity. And metals like to lose electrons, become isoelectronic to the nearest noble gas. So what does sodium want to do? It's going to lose one electron to be like neon. Does that make sense? The nonmetals are the opposite. They like to gain electrons. They're dull, they're brittle, and they're insulators. You can't hammer them into different shapes. They're just too brittle. So nonmetals like to gain enough electrons, become isoelectric to the nearest noble gas. So chlorine is going to gain one electron to be like argon. Sulfur would gain 2. Phosphorus would gain 3. Arsenic would gain 3. And then we have the metalloids or semi-metals that share some properties of both. Okay. So questions so far? So the periodic table that I like is the real one. It's the one that you find in real chemistry labs. It's not the kind that's used in textbooks and stuff. If you can open up most textbooks, they have this skeleton of a periodic table with no information on it. But the whole purpose of a periodic table is to put a whole bunch of information on it. So they totally defeat the process. So in this one, if the symbols are black, that means it's a solid at room temperature. If it's blue, you can see there are liquids. So there's not very many liquids. So bromine is a liquid. I have it in the lab. It's a very reactive liquid. I have to change the cap on it all the time. And then mercury is a liquid. Mercury is a metal. It's a liquid metal. Then the gases are red. So with the gases, you can see that hydrogen is a gas. You can see that nitrogen and oxygen are gas. Fluorine is a gas. And look at these. Why are they called the noble gases? Because they're in red. They're all gases. That's why. Then we get to the hollow letters. Those are the ones that are man-made. They do not exist on planet Earth. We make them in the laboratory. Most of them don't last more than a fraction of a second before they fall apart again. And the reason is you just can't put that many protons into a nucleus. The nucleus becomes unstable. So you should know some of the names of the families or the groups. So group 1 are the alkali metals. That would be sodium and such, right? Group 2 are the alkaline earth metals. would be beryllium. You could call it the beryllium family if you wanted. Then you should know the halogens, because those are used in halogen lamps and all that kind of stuff. People know that. And then finally, you should know the noble gases. These are the inert gases and noble gases. They don't react with anything. And I remember being told, oh, you're supposed to memorize all of the names of the families. Like, I remember this group here, starting with oxygen, was called the chalcogens. It's like, what the heck does that have to do with anything? But now we can just call it the oxygen family.
I have a question. Is for the halogen, is that group 17 or group 7?
Is group 7. I use group 7 because that describes the number of valence electrons.
Gotcha.
Yeah. So if this is the oxygen family and this is the helium family, then altogether it's called what? That's right, the atoms family. Get it? So your question about the different numbering system, I'm talking about it right here, and it's kind of interesting. So IUPAC is the acronym for the International Union of Pure and Applied Chemistry. So I'm a member of the American Chemical Society, which is also a member of IUPAC. And so they meet every 5 years or whatever, and they get together, and there's a bunch of old people drinking tea and wine or whatever, and they sit around deciding how to change things, how to accept numbers for things. And one time they came up and said, well, we're gonna change the meaning on the periodic table. So originally, all the ones that were up like this, right, were given letters A. And all the ones that were recessed down here were given the letters B. And that was very convenient because you could tell students, oh, the A groups are representative and the B groups are non-representative. And they came along and they changed it. So the Europeans were like, oh, okay, they changed it. We follow the rules. And the American chemists just said, no, we don't like it. We're not doing it. And then IUPAC had a problem because the Europeans wanted to follow the rules, the new rules, but the Americans are rebelling again, because we rebel against everything, don't we? So then IUPAC tried to save face by coming along and say, oh, we won't use A and B, we'll just number 1 through 18. And the Americans said, no, we're not doing that either. We like it the old way. So now we have 3 versions, and that's the reason why. It's because the Americans won't comply. Numbering at 1 through 18 does not help students learn anything. So for example, you were asking about group 7. Why is it numbered 17? Well, now you know why. But the reason why it was originally called group 7, because there's 7 valence electrons in every single member of that family. And that 7 valence electrons, when we get into another chapter, means something that helps us decide how those elements in that group will behave. Anyway. Well, yeah, scientists can't agree on everything. And what that does then is like make the public a little bit worried, and they can't trust science. Because, well, why do you keep changing stuff? It's like, well, we changed it because we think it needs to be better or something. Then anyway, we have a couple of trends in the periodic table that we should be aware of. One is called the ionization potential. So this is the energy required to eject one electron from an atom when the atom is in the gaseous state. So here's gaseous sodium. You hit it with energy, basically a voltage, and you try to get the electron to come out. And the first ionization potential is given on side 2 of the periodic table. And what we find is that ionization potential increases. In other words, it's harder to get the electron to be ejected as you go across the periodic table and as you go up the periodic table. So I tend to think of this as a vector. So here's the periodic table. So it takes more energy to eject the electron as you go this way and as you go this way. So I just say, okay, it goes that way. So that means that the easiest atom to take an electron away from is going to be francium. And I'm going to ignore the noble gases because they're not chemically reactive anyway. And I would say the one with the highest energy required to eject an electron would be fluorine. So hopefully you won't forget that, because those are the 2 F words on the periodic table. You guys do know what F words are, right? If not, come down to Waimanalo Beach Park on the weekend. One of the favorite words of my whole family over there. So the next one is electronegativity, and notice it has the same trends. So electronegativity was calculated. It was put together by Linus Pauling because ionization potential was not a very practical concept. Here's the reason why. Gaseous state, we don't think of sodium, metal, as a solid. It's not in the gaseous form. When you're thinking about doing biology and stuff like that, you don't put everything in the gaseous form before you do your biology. So it wasn't a very practical number. So what Linus Pauling did is he decided to do a calculation. So he took an element and looked how it bonded with other elements. And so he looked at several different ways that it bonds and found in nature, and he came up with a value called electronegativity. It's also given on side 2 of the periodic table. And you see the one with the lowest electronegativity is francium, the one with the highest is fluorine. And really what that means is that if you're francium, anyone on the periodic table can take your electron away. If you're fluorine, nobody can take your electron away. So if you're any other element and you bond with fluorine, fluorine is taking your electron away. And the element with the next highest electronegativity is oxygen. So other than fluorine, if you are any other element on the periodic table and you form a bond with oxygen, oxygen is taking your electrons away. When you lose electrons, that's known as oxidation. So yeah, oxygen is a very powerful oxidizing agent. It takes electrons away from almost everything. When you inhale and breathe in oxygen, what is that oxygen going to do? Take electrons away from whatever it is that you're biologically reacting with. So for example, you eat reduced forms of carbon called food, and then you exhale carbon dioxide, which is pretty much the most oxidized form of carbon. So the oxygen you breathe in is being used to oxidize carbon and other compounds. When that happens, you get energy from it to run your body. So metals try to give away electrons to become like a noble gas. So they have lower ionization potential and lower electronegativity. So now we can say that metallic properties actually increase in the exact opposite direction as electronegativity. Whereas nonmetals, which want to take electrons, will go in that same trends as electronegativity increases. Does that make sense? So this little thing right here basically shows you the size of elements and their ions. It's not a complete of the periodic table, but it's kind of instructive. So let's look at this. Here's lithium. What does lithium want to do? It's right here on the periodic table. It's a metal. Metals like to lose electrons. How many does it like to lose? Well, the only charge there possible is a 1. So what lithium wants to do is lose 1 electron to become like a noble gas. Look what happens to it when it loses that 1 electron. It goes from 152 picometers down to, I think that's an 80. But just visually, look at that. That is a dramatic change. You take away 1 electron, and now the diameter of that anion is it's way smaller than before. And some people would think, oh, that's because you take away the outer peel of the onion, right? So the onion gets smaller. Well, that's overly simplistic. What I'll tell you is the major determination of the radius or the diameter is about attractive forces. The attractive forces between the nucleus and the outermost electron is what determines how far out that furthest electron is. It's all about attractive forces. The universe works upon attractive forces. That's why I wrote a whole chapter on attractive forces, which we'll get to much later. But look at the dramatic change over here. Then if we go to the other side, what do nonmetals do? Here's fluorine, for example, it's 64, I think. And then what does fluorine want to do? Gain 1 electron. It's right here. If it gains 1 electron, then it's like the noble gas, right? That's what it wants to do to become stable, like the noble gas. But look what happens. The radius increases by more than a factor of 2.
Well, isn't it because electrons like stay really far away from the nucleus?
That's true. But when I try to put this electron onto this one right here, what's on the surface of this atom right here? It's other electrons. So I'm taking an electron and I'm trying to put it on something that's already negatively charged. It's going to be repelling it. So even though it seems like you're peeling an onion or adding another layer to the onion, that's not even really a factor. What drives all this is attractive forces and repulsive forces.
Okay.
So now if we look at the trends over here, as you go down a group, right? Oh, it gets bigger and bigger and bigger. That makes sense because more protons, so therefore more electrons, right? What happens when you go across a period? You're adding more protons and more electrons, and you're thinking it should get bigger then, right? Oh, what the heck? It's getting smaller. That's crazy. So you're adding more protons, more electrons, and it actually gets smaller. Okay, well, now I have to explain that. You guys have it easy. You just have to remember it. I have to actually explain it. So let's take lithium. Its radius is 205 picometers. Beryllium is 140, right? So a dramatic decrease going this way. So this has 3 protons, this has 4 protons. So how the electrons are arranged is that in the first shell, you can get 2 electrons in there. That's all. Now it's full. Then its 3rd electron is in the next shell. So what I'm going to do is very simple. I'm going to take these 2 inner electrons and simply negate 2 of the protons in there. I'm simply going to cancel them out. And then I look at the overall attractive force between this outermost electron and that 1 remaining proton in there. It's simply 1 proton being attracted to 1 electron. Now I go to beryllium. It has the same arrangement of electrons. So I get 2 electrons in the inner shell. Now I got 2 in the outer shell. So the attractive force between the outer shell, which has 2 electrons, I'm going to negate 2 more electrons and protons out. And what is the net attractive force between the nucleus with 2 protons and the outermost shell, which is 2 electrons, is 2. So you see, as you go across, the attractive force actually increases, which causes the smaller radius, the smaller diameter. What happens when you go down a group? So below lithium is sodium. And yes, it does get bigger, but not substantially bigger. What's the deal here? So here I got 10 inner electrons. I'm going to use that to cancel out 10 of the protons. And what is the net attractive force? Still 1 proton to 1 electron. Does that make sense? So when you go down a group, the net attractive force analyzing this matter doesn't increase. When you go across a period from left to right, the attractive force between the nucleus and the outermost electrons actually increases, causing its radius to decrease. So to summarize, when you go down a group, right, you're putting electrons into different shells. Here's shell 1, shell 2, shell 3, right? But when you go across a period, you're putting electrons into that same shell. So that same position, that same shell gets more and more negatively charged. At the same time, the nucleus gets more and more positively charged.
Excuse me, Professor.
Yeah.
I'm still a little unclear on this. So if moving left to right on the periodic table, the attractive forces increase because the valence shell of the electron has more, the valence shell of the atom has more electrons in it.
Right.
Than if you were to go down the periodic table. Is that correct?
So look, here's shell number 1. Here's
Yes.
shell number 2, right?
Yes.
So shell number 1 was unaffected, right? Shell number 2 got more charge in it,
Yes.
as did the nucleus.
Right.
But when I'm going down a group, I'm putting electrons not into the same shell, but into higher shells. So they are further away.
In short, I could say that if I go right on the periodic table, then I'm dealing with more stable atoms because the outer shell is balanced?
No, not necessarily. So we're just looking at atomic radius now. We're not looking at chemical reactivity.
Okay.
Yeah.
Okay. So it just has more electrons on the outer shell. Oh, I should just remember that.
Right, right. You're putting electrons into that same place. So that same place gets more and more negatively charged. At the same time, the nucleus gets more and more positively charged.
Yes. Okay. Thank you.
But anyway, thanks for pointing that out, because I often say this would be a really great essay question.
So,
1,000
Professor,
words or less. Explain why the radius of beryllium is smaller than that of lithium.
so is it safer to say that the more electrons you have, the bigger the radius?
No,
Or not really?
because that's the opposite effect when you go from left to right across a period,
I see.
which is why I have to come up with this long explanation. Yeah. So ultimately, I'm trying to explain this, right? As you go across a period, it's not getting bigger, it's getting smaller. That's why I had to explain that.
Oh, so that's due to as you're going further right, and there's more electrons in the like outer shell and more
Yes.
protons inside the atom. Like there's like a more of a like a force, and that's what like squeezes them together and makes them smaller.
Exactly. Yep. Mm-hmm. Yeah, it's a lucky thing we won't have any essay questions, huh? So anyway, that's pretty much it for the chapter. I wanted to add this because I put this timeline together and it was like blowing me away. So 11,000 BC is when they say the Copper Age started to happen. And malachite stone is a kind of stone that's kind of greenish and stuff. So if you put it into a fire, this copper, this silvery, shiny metal just starts oozing out of it. It's a very soft metal. And you know how people, they would build fires to keep, predators away at night, keep warm, all this kind of stuff. And they wake up the next morning, it's like, oh, what is this coppery stuff? I mean, I can use it to do stuff with, right? You can shape it into things. So it's not really good to make a weapon with or anything. If you were to try to make a sword out of copper, some guy with a stick is going to kill you. So probably the very first thing that was used was what? Probably jewelry, huh? Now look how long it took for the Bronze Age to begin. Okay, so the Bronze Age took a long time to happen. So they took copper, which they already knew about, and they found that if they mix it with tin, they could get bronze. And now you can make swords. That is strong enough. But look, it required a much hotter fire. So how do you make a fire hotter? Well, you blow oxygen into it, right? That's how you make it hotter. Then a lot more time goes by and you see that, okay, now gold becomes rather prevalent in human societies. How do they discover gold? Well, they just find it that way. They find it as a pure element. So you're walking through the riverbed, what's this shiny golden thing? And you pick it up and it's just like, it's beautiful and it stays that way. So they thought it had religious significance and all this kind of stuff. And now you needed swords to get more of it and to protect what you got. Then look, almost immediately the Iron Age begins. You take iron ore, which is simply a rock, and you have to purify the iron out of it. So you melt it out of it, and then you retain the iron. The process of smelting required a much hotter fire, so you had to invent the bellows. So the bellows pushes oxygen into the flame on upstroke and downstroke. And now you have extremely strong swords. So if you have an iron sword, you will beat somebody with a bronze sword. Then it took another couple thousand years to get steel. So what you do is you take iron and you impregnate it with between 5 and 10% carbon. A little bit hotter of a fire, you get steel. Now you have really sharp swords. And if you're ever to look at one of those educational programs about making steel, like one thing that's really interesting is the technology that went into samurai swords. Tremendous technology. So they didn't really know the chemistry that they were doing, but that didn't stop them. They had the, they let the technology drive it. So the more carbon you put in there, the harder it gets, but then the more brittle it is. So to prevent the swords from being broken easily, from being hit sideways, they actually took mild steel and they wrapped around high carbon steel around it in a very specific way. So the cutting edge was very high carbon. And as you get away from that cutting edge, it was less and less carbon. Very amazing technology. I was watching this other show where they were trying to reproduce what some Viking swords were doing. So historically, they were finding these Viking swords, maybe 1 out of every 100, or even less than that, had a certain stamp on it, had a certain insignia on it. And these swords were actually made out of steel. And this was during the Iron Age. So they tried to reproduce how these were made. And it's quite amazing the technology that they had. So during the Iron Age, some of these Vikings could just go in there and basically chop other people's swords up. They were feared. They were crazy. So anyway, so gold is valuable because it's rare and stays shiny. Chemically, that means it doesn't form oxides. And so it has religious significance. Tried to put some stuff in here about that. But then, is gold really rare? So I found this data from 2009. And they estimated that in all of human history, this is how much has been mined, 165,000 metric tons. That would make a cube with 20-meter sides. It would fill 3.4 Olympic-sized swimming pools. So now you get some kind of a handle on this. It's about 3.5 Olympic-sized swimming pools is all the gold that's ever been harvested on planet Earth. But tell me, is it rare or is that not rare? Kind of an interesting concept, huh? So India buys about 1/4 of the world's gold. Indian households contain about 11% of the global stock, mostly as jewelry. And does that mean that India is a very rich country? They got a significant amount of the gold. Are they a rich country? The answer is no. So Indian gold is cut and not 100% gold. It's also very thin. They use a lot of gold plating and stuff like that. And it's extremely important to them religiously and sociologically. Jewelry is handed down from mother to daughter to down that lineage. I remember when my mother passed away, my sisters really didn't want the jewelry. It's like, oh, we don't care. So new gold is about 50% jewelry. Most of the rest is investments. And about 10% goes to industrial products. Okay. Here's a couple of, maybe you call them a joke, I don't know. I'll let you decide on that. The chemistry has some interesting people there. Charles Hall invented a method for extracting aluminum from aluminum ore. He did that at home in his woodshed. And then he graduated from this college in Ohio. And he goes to the college and says, oh, can I use the college lab to like perfect this method and get a cheap method for producing pure aluminum? And said, yeah, okay. So then he gets this extremely cheap method for producing aluminum, because before that, aluminum was extremely rare. It was hard to get. It didn't last forever either. So he couldn't get any financing. So he and his friends started the Pittsburgh Reduction Company, later became Alcoa. So he made millions for himself, for his college. He created a brand new industry. No aluminum, no airplanes, no all kind of stuff you can think of. And Herbert Dow, at similar time, he got his degree in engineering. So he, like most of the people of that time, everything was about steam engines. So they were trying to put railroad tracks across the United States, which really was significant in building up the United States. I remember one of my friends, he was an Indian guy. His father was a chemistry professor in India. He was a biochemistry professor here. He told me one of the best things that actually maybe the only good thing that the British ever did for India was to put railroads across the entire country of India, so people could go from one part to the other part. But anyway, he stopped doing that, and he figured out ways to get pure bromine and pure chlorine, started Dow Chemical Company, second largest chemical company in the world, all because he learned how to do 2 purifications and made it work. Yeah. So just some jokes over here. I don't know if you guys like the jokes or not. But this one is kind of funny. Here's the Gilbert Lab technician set for girls. So in 1958, Gilbert Company came up with this lab technician kit for girls, but they had already had the chemistry set for boys. And so nowadays people look at this, it's like, oh my God, they were so anti-women back then and everything. 1958, this was actually a really important step for trying to get women into science. It's unfortunate they made it into a lab technician set instead of like a chemistry set for the boys. But if you go back and you look at all their company records and everything else, why did they make this? Because they were purposely trying to get girls into science. In about the same period of time, they actually had this, the Gilbert Uranium-238 Atomic Energy Lab. So they actually would put radioactive uranium in this kit for kids, and they would be able to learn how to detect radioactivity. And it came with a mail-in card. If you ever ran out of uranium-238, you put a stamp, mail this thing, and they'll send you another package of uranium-238. Hopefully you think that's kind of unbelievable, but
Where do you get uranium-238?
uranium is, yeah, that's an interesting question. I talk about this a lot. If you look on the periodic table, here's uranium right here. You can find it on planet Earth. Anything bigger than that, you cannot find it on planet Earth. So uranium is important because it can actually be mined as uranium ore. Now, it turns out uranium-238 is not that radioactive, but my God, how ridiculous is that to expose your children to any amount of radioactivity? Interesting,
That's
huh?
very, very interesting.
So by the
Can
way,
you- in the United States?
when they were bombing, Micronesia after World War II, right? And so they would pull these ships up and watch these atomic weapons go off. So they would take the ship and put it sideways so everybody could come on one side of the ship and see it. And all the generals and all the important VIPs flew from all over the world to be there to watch it. And of course, they were all exposed to radioactivity. Anyway. Humans are not the most intelligent of all the creatures on planet Earth, I'll tell you that. So any questions on that chapter? It's a short chapter. So I'm going to go into chapter 6 then, which is about nuclear chemistry. And I've noticed that, man, there's a lot of faculty that I know, oh, I don't have time to cover that, so they don't cover it. And I'm like, I think it's one of the most important things. So radiation was discovered about 1896 when they found that there were certain things could expose photographic film. So in other words, they took something, put it down on the photographic film, and it would expose the film. It's like, hey, what's going on here? There wasn't even light on there. So then everybody's going around like, hey, I wonder if this is radioactive. I wonder if this is radioactive. And they found that all elements have some isotopes that are radioactive. And I probably should reword that. All elements, yeah. And in fact, this is it. I think I will do that right here. And now you're watching how I yeah. Now you just witness and edit it. So we also have some very small isotopes that are radioactive, like tritium, hydrogen, okay? And so radioactive isotopes are also called radionuclides. So what is classical radiation? So it came from this original experiment. You took some radioactive material and they put it into a lead box with a tiny hole in it. They found that lead would prevent radioactive materials from blackening the photographic film. So now the radioactivity is coming out of here. It's going through these slits. So now it's going in a straight line. Then they put it between two plates with a voltage across it. So they took this radioactivity that was coming out of the block of lead and put it into this voltage over here. And they saw that some of it was not affected at all. It just went straight forward. So you can use photographic film over here or phosphorescent screens like the old-fashioned television screens. And it would show some exposure right here. So that was called gamma radiation. And then it also split off this way. So if this is the negative plate and this is attracted to it, the charge on an alpha particle must be positive. So that was called alpha radiation. And then there was another that was deflected in the opposite direction. So this must be negatively charged because it's attracted to the positive plate and repelled by the negative plate. So classical radiation was alpha, beta, and gamma. So now we know what those are. Alpha turns out to be the helium nucleus. So this comes flying out of the nucleus of the radioactive isotope at about 10% of the speed of light, which is a huge speed. And it has 2 protons. That's why it has the symbol for helium. You can see it has 2 neutrons as well, and it doesn't have any electrons. That's why it's positively charged. So it comes flying out of the nucleus at about 10% of the speed of light. It can penetrate into your tissue about 0.05 millimeters. So what does that mean? Alpha radiation will be stopped by your clothes. It will be stopped by the layer of dead skin cells on your body. However, if you breathe alpha radiation into your lungs, the lung tissues have nothing to protect them. So radiation causes damage to your lung tissues. Turns out that the beta radiation was actually an electron. Okay? So this is the way we normally put the electron. So there's no protons or neutrons, and instead of putting down here the number of protons, it's a -1, it happens to be the charge. So sometimes it's written as beta, like alpha, like that. So beta is going somewhere around 90% of the speed of light because the mass of an electron is very small, so it can go quite fast. And where did this electron come from? It came from the nucleus. It did not come from the electrons cruising around the nucleus. It came flying out of the nucleus from a nuclear reaction. So it can penetrate 4 or 5 millimeters into your skin. Normally that protects you, but there's hard beta, which goes faster, and soft beta, which goes more slowly. When I used to work with radioactivity, if I'm working with an alpha emitter, I would simply wear 1 pair of gloves and a lab coat. When I was working with beta, I would wear 2 pairs of everything, gloves and lab coats. And gamma is simply no mass of any kind. It's going 100% the speed of light because it is the speed of light. It can penetrate and go right through your body. And all three of these are considered ionizing radiation. So when they hit your cells, they are causing damage to your cells. Gamma leaves a trail of destruction right through your body.
I have a question.
Mhm.
So when they put the lead, or sorry, when they put the radioactive material into the lead box,
Yeah.
how are they aware of it splitting? Like how? Because you can't see it. So how are they aware that there was something even going through these slits that they had made, and that it would break into three different rays?
Yeah, well, they could look at it with what is it doing with photographic film? Or if you have fluorescent paints, it would do the same thing. It would like make fluorescent paint glow.
Oh,
Yeah. So you can imagine when they're first playing with it, they were all being exposed to radioactivity. They didn't even know it was harmful at the time. All they
yeah.
knew was just doing that effect on fluorescent paint and on photographic film.
It's such an interesting concept that that an element can, like, if you hold it, that there's rays being emitted from it, and that it's like killing you, but you can't even see it.
Yeah.
It's crazy.
That's what happened to Madame Curie. Her entire lab to this day, lab notebooks, pencils, everything, totally radioactive.
Huh.
But here's a question. So your DNA is electrically neutral, right? All the atoms in your DNA are stable. Besides this heavy particle slamming into your DNA and causing breaks in your DNA, what if I very gently displace that alpha particle right on your DNA? What's it going to do to your DNA? It's going to take electrons from your DNA. What does that do? That causes your DNA to no longer be chemically stable. It's going to undergo chemical reactions, which could lead to a mutation, which could lead to cancer, which could lead to all kinds of different issues. So anyway, nowadays we know that almost every single particle, subatomic particle that you can imagine is coming at us in terms of cosmic radiation. So what is commonly encountered radiation? So here's gamma rays, X-rays, neutrinos, electrons, positrons, which are anti-electrons, protons, neutrons, alpha radiation. It's all coming flying out of these stars. So I couldn't find information about penetration into tissue, but here's all I could find. How far does it go through water before it's 50% stopped? Okay, so it just depends on a lot. Let's see. So my French colleague and I, we learned how to find stem cells in brain tissue and grow them in cell culture. I wasn't involved in it, but he actually went to people in my department, which is anatomy, biochemistry, and physiology, and one group of us runs the Willed Body program so that the med students can dissect real human bodies, right? So he got a piece of a brain of a person who had died like the day before, took it back to his lab and was able to isolate and keep stem cells from the brain alive for, I think he kept it for about 6 months. It's kind of a spooky thought, right? The first thing that dies in your brain are the nerve cells. So then you're brain dead, right? And then the helper cells, the astrocytes and stuff like that live much longer because they're much less specialized. then the stem cells basically can survive for months, if not years, because they're undifferentiated. So we were working with this company that was working with NASA, and we were actually going to take these little small 1 millimeter cubes of brain in cell culture and put them on the space station to assess the amount of radiation damage done to the brain tissue. It never happened. Largely, they didn't want to fund us as much as we needed. But anyway, that's a problem. We're protected by the magnetic fields from planet Earth because we have an iron core. Because the Earth rotates on its axis, that gives us a magnetic field with a north and a south. And it emanates out sometimes 36,000 miles into space. So much of this radiation, anything that's charged over here, is going to be deflected away from our planet because of this magnetic field. And you've seen or heard about the Northern Lights, right? Well, that's the same thing. That's what you're really seeing. So the Northern Lights moves all around like that because the movement of the magnetic field. So now when you go up in the space shuttle, you're getting between, well, you start off about 0.2 millisieverts per year, but you go up to the space shuttle, that's way more significant. So anyway, that is a problem with long-term space travel. You might be thinking, oh, what's going to stop the radiation is going to be stopped by the capsule. Like, well, no, that's not really the case. So there's lots of examples of a powerful particle banging into the space station, and it causes a shower of secondary radiation right in the capsule where the astronauts are. So they are being exposed to much higher levels of radiation. Long-term space travel is going to have to be able to solve that. So ionizing radiation is what causes the damage to our bodies. And so I get really upset when I find that some of my colleagues, oh, we don't cover that. Like, what? This is one of the most important things, I think. You need to understand what radiation is and its effect on you. So ionizing radiation does what? It ionizes things. It causes electrons to be ejected. So I'm going to do a very simple example with a water molecule. Here's the complete Lewis electron dot formula for water. Okay, every dot is a valence electron. That line right there represents 2 valence electrons in a covalent bond shared between the hydrogen and the oxygen. So, the water molecule is just sitting there, pretty happy, pretty stable. It gets hit by ionizing radiation. That causes an electron to be ejected from the water molecule. Now the water molecule is not so happy. Matter of fact, anything with an odd number of electrons is known as a radical. So this is the water radical. And what the water radical will do, because it's so extremely reactive, oftentimes in an effort to become more stable, it also ejects a hydrogen atom. Okay, well, at least now it's not charged, right? But it's still a radical because it has an odd number of electrons. So this is the hydroxy radical. There's several ways to form the hydroxy radical. And the hydroxyl radical is blamed for most cancer, aging-related diseases, radiation exposure. It is simply tremendously damaging. You hear all this stuff about nutritional companies selling you, what's the word they use? For some reason, I'm not thinking of the word, but antioxidants. So the antioxidants is not against oxygen, it's against compounds that contain oxygen, because oxygen is one of the elements that can form lots of radicals. So they're claiming that if you take their supplements, then it will help you fight production of the hydroxyl radical. Partially true. So here's another way that hydroxy radical can be formed. Here's how hydrogen peroxide is formed. And you are forming hydrogen peroxide right now as we speak. You are an aqueous organism, breathing in oxygen. You will be producing some hydrogen peroxide. The same hydrogen peroxide that you buy at the drugstore. One of the things that hydrogen peroxide can do is break down what's called the homolytic cleavage into two hydroxy radicals. So all you're doing is splitting this bond right here. One electron goes that way, the other electron goes that way. So right now you are producing hydroxyl radicals because you're an aqueous organism, you're breathing oxygen. If you are an aerobic organism, which I totally believe that you are, you have an enzyme called catalase. What does catalase do? All aerobic organisms have catalase. It's an enzyme that takes hydrogen peroxide and breaks it down safely into the manner in which it was originally formed. Anybody take microbiology yet?
Yep, I did.
You did?
Yeah, I did.
So one of the things they often have you do is they have you go around, you swab everything, right? And then you streak it on the growth media. So when you do that, you'll find out that, you know, the toilet seat has less bacteria than your boyfriend's face. And yeah, you'll find out some interesting things like that. But one of the tests that they'll have you to do is find out whether it's an aerobic or an anaerobic organism. So they take a dilute solution of hydrogen peroxide, they dab it on the colony, and if you see bubbles forming, that means it's an aerobic organism. The bubbles that you're seeing are oxygen bubbles being formed by the enzyme catalase. How likely is it that you will get a bacterial infection from, say, a tabletop or something, from an anaerobic bacteria? It's very unlikely. The reason is the anaerobic bacteria are killed by oxygen because they don't have the enzyme catalase. How do you fight an anaerobic bacteria? You give them as much oxygen as you can. Later on, we'll talk about that. You can put them in a hyperbaric chamber with pure oxygen. So how do you get anaerobic bacterial infections? Well, the anaerobic bacteria live in the dirt. They live in, kind of like polluted waters. There's not that much oxygen. So we detect radioactivity with photographic film, fluorescent paint, but also with a Geiger counter. So I wanted to show you how a Geiger counter works. So here's the detector part of it, right? So this is a metal outside. There's a metal line in here, all connected to electricity. And then there's a gas in here, an inert gas. Most likely it's going to be argon or helium, something that's inert. And then there's a window over here that allows ionizing radiation to come in. So when ionizing radiation comes in and hits those neutral gas atoms, it ionizes it. It kicks the electron out. So notice that this wire right here is positively charged. So as soon as this electron gets ejected, it's going to be attracted to this positive charge. So then it travels through the wires, goes through the circuit system, right? Through all the electronics, and comes back over here to the outside, which is negatively charged. So then, as soon as this positively charged detects that this is negatively charged, it moves towards it, and the electron jumps back on, and you regenerate your neutral gas particle. But meanwhile, the ionizing events have caused a circuit to go through here. You created current. That current is then amplified and can be used to run a counter. It can be used to run a speaker. Oftentimes, Geiger counters, you put them on speaker mode and you just go around whatever like that looking for, if the speaker goes off, then you know that there's radioactivity there. So the effects of ionizing radiation in your body are cumulative over your lifespan. So what do I mean by that? When your parents first got together and that egg was fertilized and that became you. You guys remember that when you first became you? When chromosomes were rearranged and you finally end up with the right number of chromosomes and all that kind of stuff, that was you. And you were being exposed to radiation that whole time. So now that you're the age that you are, you've had that many years of being exposed to radiation. Oftentimes they'll tell you this in biology: oh, every cell in your body has the same exact DNA sequence. Well, in fact, that's not true. If you look at the skin cells of older people, and I know you're looking at me, if you look at the skin cells of older people, you can see that these skin cells look different than these skin cells because they're genetically different because of all the mutations that's been accumulating in your body. So one of the things you always want to do is minimize your exposure to radiation. So if you're down on the beach and some radioactive drum comes washing up, what are you going to do? You're going to get the heck out of there. So here's the reason why. I'm going to try to explain this in math, but like explainable kind of math. The intensity of radiation that you feel is proportional to the intensity of radiation at the source. But that's diminished by 1 over the distance between you and that source. And look at the other important thing, that distance is squared. That means if you increase the distance between you and the source, your exposure, the intensity that you feel, will diminish dramatically. So here's a diagram. So here's the source over here, right? And say you're standing right here and D is equal to 2, okay? This is your level of exposure right here. So you're getting that much exposure. So the intensity that you feel, because D is 2 and you square it, is 1/4 of what you had over here, approximately. If I double the distance, now I'm getting only 1/16. That's a factor of 4 by simply moving away twice as far. Why is that? Because your exposure actually gets reduced, and you have all kinds of air and everything else in between you, absorbing that radiation.
So you can in fact feel radiation?
Normally you don't. If you're very close to it, it'll feel like you're burning up,
Like-
and feel hot, right?
Like the elephant's foot.
The elephant's foot?
Oh, yeah. In Chernobyl, there's this glob of radioactive molten melted steel. They call the elephants. And they say if you go close to that, you die in a matter of hours.
Yeah, wouldn't be surprised. So anyway, here's a better relationship. It's more accurate than this approximation over here. So I just want you to do some calculations so you get the hang of it, so you really understand it. So all I did is take this and I solved for intensity at place 2, right, which would be over here. So it's more moderated by this. It's more accurate than this, okay? So estimate the intensity of radiation at 2 meters if the intensity at 1 meter is 50 millicuries. So I just plugged it in, and look at that. It goes down to 13, from 50 to 13 by moving 1 meter away. What about the intensity at 10 meters? Okay, so I increased to 10 meters. Oh my God, I went down by a factor of 100. Okay. So that's what I mean by that. So I'm not going to make you memorize these equations or something like that, but like doing a math problem like that does make you really understand the concepts. Here's the last concept we have for today. When it comes to biology, what's the important thing about anything is dosage. It took them quite a while to figure out that, oh, dosage and radioactivity is important. So here were some of the original ways to quantify radioactivity, like the disintegrations per second. Look at that, 37 billion disintegrations per second. That's a huge number. And the Roentgen, it's like 1 billion, like 2 billion charges in the milliliter of air. That's just a huge number. In the X unit, basically a mole of charge in a kilogram of air. A mole is 10 to the 23rd. This is huge numbers. So we use radiation in biology. So here's the first one. A gray is the joules absorbed by a kilogram of tissue, which is about 100 rads, radiation absorbed dose. And a sievert is the number of grays times an energy factor and times a tissue factor, which is similar to the Roentgen equivalent for man. So I just want you to know the difference between something that is not a dosage and something that is a dosage. So the LD50 is interesting to look at. That means lethal dose 50%. That means you expose somebody to a chemical or to radiation, and 50% of the subjects die from that exposure. I'm not talking about 20 years later they get cancer. So the LD50 for man is about 500 millirems. For rats is about 800 millirems. For bacteria, it's about 50,000. for insects is about 100,000 because of their exoskeletons protects them, right? So humans get about 359 millirems spread over a year. That clues from all natural sources. Your girlfriend is radioactive, your chihuahua is radioactive. And that also includes nuclear and medical events, which is another 65 millirems per year. And I did an interesting calculation. If this is what we get exposed to naturally, and this is what's added because of human activities, man has increased exposure to radiation by about 22%. Here's the normal symbol. Here's another more modern symbol. I've never seen this one before. I don't understand it because it looks like a spaceship is coming. They're turning us into zombies, so run that way. But this is the same thing as this, so why do we need that? I don't know. I've never seen that. So we'll stop right here. And tomorrow we'll pick up over here. Does anybody have any questions?
So I'm just making a general question here. I mean, the sun emits radiation, and I imagine that when you go outside, you absorb some harmless amounts of radiation. Is that correct?
Oh, yeah.
So if that's being the case, if you're closer to the equator, like you're living in Hawaii, do you have a higher chance of being exposed to larger amounts of radiation than if you lived in Alaska?
Well, the major factor there is electromagnetic fields on planet Earth. So, yeah, we get more sunlight at the equator, which includes bad stuff like ultraviolet light, but that's not radioactivity.
Okay.
Do we get more neutron type radiation? Maybe slightly, but probably insignificant. Biggest factor is the magnetic field of the Earth.
Uh-huh.
Yeah.
So maybe the places where you can see the aurora borealis are at higher risk?
Yeah, maybe. Yeah. But it's hard to assess because everything is constantly moving. The magnetic fields are moving. Fluxes in the corona of the sun are changing all the time. And
I see.
yeah.
Very interesting.
Yeah, you might be able to find that information somewhere. I never looked for that.
Yeah.
But yeah, being alive is dangerous, isn't it? Okay, well, I'll be sending out an email asking for who wants to take the exam tomorrow. And then that morning, when I get the email from you, then I'll send you the current password for the exam. Okay. Otherwise,
For Chem 100, we should just sit tight.
I'm sorry?
For Chem 100, we should just sit tight for the moment.
Oh yeah, sure. Yours is coming up.
Okay.
Yeah. Okay. Well, I guess we'll end it here. You guys have a great day.
You too.
Look out for radiation now. Okay, take care.
Thank you. Bye-bye.